The interaction of downflow and pier profile by particle image velocimetry. Abstract. This manuscript at a controlled laboratory level focuses on interaction, regarding an obstruction structure as a bridge pier, when water flow hits it. Within a scale hydraulic channel, immersed reflective tiny spheres in a laser lighting, it was observed the upstream downflow behavior, before 3 different pier profiles proposed, and utilizing the known particle image velocimetry technique, from a superior view, it was possible to obtain qualitative data from downstream turbulence degree, respectively. Therefore, in this manner, pier improvements could be considered in order to reduce the theoretical local scour. Keywords: downflow, particle image velocimetry, pier, profile, scour. 1. Introduction. The theoretical local scour, in general terms, occurs due to upstream water flow, when obstructed by pier, divides, going upwards and downwards known as downflow, up to hitting the bottom and subsequently surrounding the pier profile surface. 3. Causing a turbulent flow, generating a sort of vortex called the horseshoe coming from a strong gradient of pressure and being the main cause of soil erosion. 8. This behavior is similar to a vacuum cleaner suction, accumulating sediments further downstream. 6. Fig.1 shows the theoretical typical behavior of water flow interacting with an obstruction pier. Fig. 1. Water flow interacting with obstruction pier. 2. Local scour. The scour is a result of erosive action of water streams on the bottom channel, especially in rainfall times when rivers' flow rate is higher. 10. Local scour corresponds the sort of failure. Number 1. Faces expensive repairing costs. 4. Terminating service life of a bridge prematurely, and even worse, cases where it collapses. 1. Causing traffic delays, road closures, and unfortunately human casualties. 5. It is important for a bridge over a water open channel to consider countermeasures for downflow and hydrodynamic profiles, in order to protect it from scour that may occur in that particular section, attempting to obtain the best design. 7. Fig. 2 shows evidence of horseshoe vortex scour in bridge pier. IJERT 9 is 050365 www.ijert.org. Published by International Journal of Engineering Research and Technology, IJERT. www.ijert.org. ISSN 2278-0181. Volume 9, Issue 05, May 2020. Fig. 2. Evidence of horseshoe vortex scour in bridge pier. 3. Particle image velocimetry. The known one as particle image velocimetry, PIV, it is a common utilized optical method to measure the velocity of fields, which is a real-time, effective and non-destructive procedure. 9. Fig. 3 shows the PIV equipment and water channel. For subjects such as hydrodynamics and dynamics aspects, it observes the velocity of fields into a movement flow, becoming important for a variety of situations. The essential basic experimentation is measuring the velocity of flow by vectors direction for the best understanding. PIV is utilized in several research fields. Commonly this technique measures the instantaneous velocity distribution in 2 dimensions, by means of photographic movement determination of immersed water flow tiny spheres in a plane during a pretty short time lapse. 2. PIV applies to measure the distance, s, immersing particles, tiny spheres, into a flow in movement during a time lapse. T. Where U means the velocity obtained under the following EQ. 1. Fig. 3. PIV equipment and water channel. 4 methods. At controlled laboratory level was utilized the followed equipment: charge coupled device, CCD, camera previously calibrated. 532 nanometer green laser lighting, reflective 9-13 m spheres, water immersed in hydraulic transparent plastic channel with 1.5 HP electric pump, 0.50 m long, 0.15 m deep and 0.15 m width. 3 different 0.02 m thickness pier profiles were proposed. Squared, cylindrical and bladed. Afterwards videos were obtained from superior view water flow movement when obstructed by pier respectively, Each video was recorded taking for vector calculation a 24x24 pixels window at 700 microseconds, 40 images, then the final result was the average for data, which were processed utilizing a visualization software Lavizion DAVIS8 and programming Octave software as post-processing for vectors direction and vortex imaging. Water flow level was 0.15 m, applying a velocity of 0.117 m/s, generating a flow rate of 1.5835 L/s, hence a Reynolds number obtained was Re equals 4374.37, Re greater than 2000 is considered turbulent flow, under the following EQ, 2, where equals water density, V equals water velocity, R equals hydraulic radius and equals water dynamic viscosity. 2. 5 imaging results as following. Fig 4, A, B, and C, shows photographs upstream downflow behavior utilizing immersed spheres and green laser lighting for the pier profiles proposed. Then Figs 5, 6, and 7, shows downstream water flow behavior, PIV superior view images for squared, cylindrical and bladed piers respectively, from which ones the third was the better hydrodynamic profile. Fig 4, A, B, and C. Regarding downflow, similar behavior for squared and cylindrical pier, bladed pier no significant evidence. Fig 6. Cylindrical pier downstream water flow behavior. Fig 7. Bladed pier downstream water flow behavior. 6. Conclusions. In a qualitative manner, squared pier profile corresponds to the worst of them, due to turbulence and vortexes could be observed immediately behind it. Cylindrical pier profile shows an evident improvement because its roundness, being softer, it is a commonly profile utilized in the real field application for bridges construction. Both previous profiles, appreciably generate the called condition of downflow, therefore attempting to reduce it, the bladed profile is obtained, showing the lowest turbulence and vortexes of 3 ones, as seen in figures. The PIV is a useful technique for this research, looking for a profile that provides enhancements for turbulent flow reduction, hence minor scour probability, at least at laboratory level. 7. Acknowledgements. We want to thank ENG Carlos Eduardo Sanchez Ramirez, Centro de Aeroespacial de la Facultad de Ingeniería, Universidad Autónoma de Chihuahua, Mexico.